In this video, we will be going over what the Graph protocol is, what it does, and how you can use it to quickly build reliable APIs that power your decentralized applications. Let us first look over the actual problem that the Graph protocol tries to solve. See, a user-facing dApp might need to serve large amounts of blockchain data to users reliably and quickly. And using libraries like Ethers.js, a dApp can connect to the blockchain, but the network might be millions of blocks long, and the data that the dApp needs might be scattered along the network, indexed in a way that makes it difficult to fetch it instantly. This might make for terrible user experience, and this is where the Graph protocol comes in. The Graph protocol provides you these tools to build and host APIs called subgraphs that sit between the blockchain and your dApp. While creating a subgraph, you define the exact structure of how your API should store and serve data to your dApp. This means that your dApp no longer has to connect directly to the blockchain, and it no longer has to parse through and organize the data that is returned from the blockchain in real time. All this heavy lifting is done by your subgraph behind the scenes, which considerably improves the reliability and speed of the data that is being served. Now, the Graph protocol provides us with three main tools. Number one, the Graph CLI. The Graph CLI is a command line tool that helps us in initializing new subgraphs as well as testing, compiling, and deploying existing subgraph projects. Now, the GraphTS library is a collection of APIs made by the Graph protocol to make it easy for developers to interact with their local graph node or store data from networks like blockchain or even IPFS, and also provides us with several tools to read and parse data that we're collecting onto our subgraphs database. The indexer node is the main code base that ties everything together. To deploy a subgraph, you need to compile and run the indexer node on a local computer or on a computer on the cloud. The indexer node is where you deploy your subgraphs. To get started, you need the Graph CLI before anything else. To install it onto your system, run any of these two commands. Now, once you have the CLI installed, you can create a new subgraph. To create a new subgraph project, open your terminal in a new directory where you would like to create your subgraph. Run graph init to initialize the new project. This starts a CLI in our terminal and we need to fill it out. In this video, we will create a subgraph for the Bored Apes NFT contract, which is deployed on Ethereum mainnet. So we need to take care of three main entries while filling out this form. Make sure to select the network carefully. Number one, here I've selected mainnet as you can see on the screen, which is code for Ethereum mainnet, but the graph does support networks like Polygon and Binance. So keep that in mind. Now, if you're using a relatively recent version of the Graph CLI, the start block is fetched automatically for you if possible. Each contract on the blockchain is deployed at a specific block, and it does not make sense for our subgraph to index data from blocks further back than that. So make sure to find the correct value for your start block, for the start block of your contract that you're trying to index, if the Graph CLI cannot fetch it automatically. And if this value is not configured, your subgraph will start indexing from the very first block, the Genesis block, which is just hella inefficient and just not good. Now, lastly, make sure you have entered the correct contract address for the smart contract that you're trying to index, since that address is what the CLI will use to fetch the ABI of your smart contract. Now, before starting with the actual coding, I want to take a moment to explain to you how a subgraph actually works once deployed. Now, this diagram might seem a little weird, but just bear with me, alright? The dotted line here represents the addition of new blocks to the blockchain that we're working with. Could be any network like Ethereum, Polygon, Binance. The block N represents a block that was added sometime in the past, an arbitrary amount of time in the past. And the block T is a block that was added just now. Alright. Now consider a smart contract A whose data we want to index. And the data point P is the actual data from within the smart contract that we want to index. For example, for an ERC-721 contract, P could represent each time an NFT was transferred from one address to another. We want a subgraph to track each and every such token transfer from this token contract. Once you have successfully initialized your subgraph project, you will need to work with three main files. Number one, the schema file. This is used to write entities using the GraphQL definition language. A schema file basically defines the structure of how your subgraph will store and serve data to your DApp. Does not contain any function definitions. Now, a subgraph manifest or the YAML file basically keeps a track record of the key configuration values of your subgraph, the entities you have defined, the start block, the smart contracts you are working with, alongside other things. Number three, the mapping file is where you write the main functions that define the core logic of how and when your entities will index new data from the chain. All of this will become more clear as we discuss more about it. Let us first take a look at the schema file. I have deleted all of the boilerplate code that the graph CLI generated for me. An entity is declared using the type keyword and marking it as an entity. An entity is basically a collection of key value pairs that detail the kind of data we want to index. For example, we want the Bored Ape entity to store data about each individual ape from the Bored Apes contract, the token ID, the original owner, the current owner, and so on and so forth. This is how our entity will be defined to reflect that. These data types are taken straight out of the graph's documentation, and you can look into that documentation for a full list of the data types that are supported in this GraphQL definition. Before moving on, I would like to show you how our entities define the structure of our subgraph. This screenshot is taken from a subgraph that was already deployed. On the left hand side, you can see how I queried the Bored Apes entity, and on the right hand side, you can see the response that was returned to me by my subgraph. Each instance of the Bored Apes entity contains data about each NFT from the Bored Apes smart contract. We can similarly define an entity wherein each instance of that entity will contain data about, say, a particular transaction when a token was transferred from one address to another. Let us look into that now. Let us define two more entities. The transfer entity will be used to index the transfer history from the Bored Apes smart contract. Each instance will contain data about a transaction which involved any Bored Apes being transferred from one address to another. Take special note of the immutable flag. When an entity is marked immutable, any instance of it, once initialized, cannot be edited. Think about it. We want a Bored Apes entity to store the latest data about each NFT from the contract, which means the new owner field should be updated every time that NFT is transferred from one address to another. So we cannot mark this immutable because we want it to remain updatable for the future. The transfer entity, on the other hand, will simply store transaction data about some particular transaction that happened in the past, and that data cannot be changed, hence marked immutable. In this entity, we want to store the transaction hash whenever an NFT is transferred, the token ID of the NFT being transferred, the block number that contains the transaction, the previous owner, and the new owner, and that is it for this one. Lastly, we want to define a property entity. Each instance of this entity will index metadata of a Bored Ape for a particular token ID. A Bored Ape may have any number of these 7 properties: image, background, clothes, earring, eyes, fur, hat, and mouth. Which means that some of these properties may be null, not zero. I'm talking about null. For example, I saw that many apes did not have a hat. This data, by the way, is not fetched from the blockchain. The IPFS metadata for this collection is hosted on IPFS. The graph allows us to conveniently fetch data from multiple networks like IPFS and Arweave simultaneously. Right, and one last thing I want you guys to notice, some of these properties from the entities are declared with an exclamation mark, and you'll note that these are not declared with an exclamation mark. The properties that are declared with an exclamation mark means these values cannot be null. For example, a token ID for any Bored Ape may be 0, but it cannot be null, right? But in the case of a property entity, some of these fields may be null, so we cannot mark them with a exclamation mark. That's it. If you initialized the project like I did, you'll notice that the Graph CLI generates a boilerplate YAML file for you. But whenever you make changes to the schema file or the mappings file, those changes need to be reflected in the YAML file, the configuration needs to be up to date or your subgraph won't compile. For example, we need to tell the YAML file that we're using IPFS, right? Because we're indexing data from the IPFS network. To declare it as such, you need to declare an experimental feature and call it IPFS on Ethereum contracts. That is how it is declared. Secondly, we need to update these entities because we changed the default entities to these three. And secondly, we need to define our event handlers. Now, I'll talk about this more later, but for now, know that we only need one event handler pair. We'll index all of the data that we need from the Bored Apes smart contract by leveraging its transfer event, which is emitted every time one Bored Ape is transferred from an address to another. What an event handler is, an event handler is a function that we define, and when a subgraph is deployed, this function is triggered every time this transfer event is emitted from within the contract. So our subgraph watches out for whenever this transfer event is emitted from the smart contract that we're watching out for, and whatever logic is included in this function that is executed because this function is triggered in response to this event being emitted on chain. Now we have defined our schemas, we have configured our YAML file. Whenever you do these two steps, remember to follow that up with this command, graph codegen. This will generate some helper code that we will use to define our mappings. And when you run this, okay, I am in the wrong directory and I need to be inside the target directory, right? We created the BAYC directory and inside there we created the subgraph project. So we need to be inside there and graph codegen. This will generate again some helper code that we will use later on. Before we get started with the mappings file, which is really the heart and soul of a subgraph project, I want to take a few moments to talk about the way the mint and transfer functions work in the Bored Apes contract. But even before that, I would like to point out that it is a damn good idea to be familiar with the smart contract you are indexing before even trying to write a subgraph for it. Your familiarity with the base data source that you are working with can really help in fleshing out your code and understanding of the whole project. With that being said, let us take a look at the transfer function first. Nothing fancy, but the part that is relevant to us is the transfer event being emitted at the end of the transfer function. This transfer event puts out three values: the recipient's address, the sender's address, and the token ID of the NFT that is being transferred. This transfer event can be easily tracked by off-chain entities, which is what the graph protocol is doing. Once our subgraph is deployed, it will check each and every block of the Ethereum mainnet that is being produced to check if this transfer event is being emitted on chain in any of those blocks. If this event is being emitted, it will trigger the handle transfer function that we declared in the YAML file, and you can pause and rewind the video to check that out. We have yet to define that handle transfer function, which is what we will do now. But keep in mind that whenever this transfer event is emitted, our handle transfer function will execute and whatever code is inside there will get executed. Fairly standard transfer event, right? But what about the mint function? Now take a close look and you will see how the code base allows us to leverage the transfer event to track new mints. Whenever the transfer event is emitted as part of the transfer function, the sender's address is set as the address of the person transferring that NFT. So if Alice transfers a Bored Ape to Bob, Alice's address will be the sender's address, fairly standard. But when the same event is emitted as part of the mint function, the null address is set as the sender's address. This means that whenever we see a transfer event with the sender's address set to 0, what we're actually looking at is a new mint. Think about how powerful that is for a moment. We can derive data about two separate function calls from a single event. This means we need to define only one event handler, which we have named handle transfer, to track both new mints and transfers. So mappings are essentially the functions you write to parse through the actual on-chain data and convert that data into the form of the entities that you defined. In our case, we are writing an event handler called handle transfer that will update the state of the subgraph whenever the transfer event is emitted on chain. This is how you declare that function. That function takes the transfer event as a parameter, and we have not defined anything inside it, but we've imported some libraries that the graph provides us. For example, we can use this to access logs of that transfer event that is emitted. We can use this class to access actual functions from within the smart contract, and these are just abstractions over our entities that we can use to manipulate those entities as we see fit. These libraries are some helper libraries that will let us parse through IPFS metadata, which we will fetch from the IPFS network. Let us work on the transfer entity first. First of all, we create a new instance of the transfer entity using the new keyword. Whenever we initialize a new instance, we have to populate it with a unique ID. In this case, we are just concatenating the corresponding transaction hash with the log index to create a totally unique value. And after that, it really is very simple. We can use event.params to access the specific parameters of the event that we're looking at. So we can use this to get event.params.from. If you remember, this is the sender's address. This is how we access the recipient's address, the token ID, block number, and so on. And we just populate them into this instance of our entity. So our transfer entity had these fields, right? ID from to token ID. We just feed the data that we get from this event into our entity. And after that is done, we do transfer.save. The save function permanently stores this new data into our subgraph database. Next, we initialize a new instance for the Bored Ape entity. Now, the contract address variable is a way for us to access the read-only functions from the Bored Ape's smart contract. We do this using the bind address, which binds the address of the event. Like we're looking at events from the Bored Ape smart contract, right? So we'll only be looking at events emitted from that particular smart contract address. So whatever event we're looking at, the address will correspond to the Bored Ape's smart contract. So we bind that address to this variable, and we'll be using this later on. Now this instance of this entity is initialized using the token ID that we fetch from the event. And after that, we need to perform a null check to make sure whether or not we have encountered this instance of the Bored Ape entity before. Okay, so this is a good concept, and it took me a while to grasp it. I'll try to simplify it for you as much as possible. So let us say the Bored Ape smart contract was deployed at block n, right? So that is where our subgraph starts indexing from. Block number n, the contract is deployed. Let us say the first NFT was minted at block n plus 5. That means, let us say the token ID was 1, right? So our subgraph goes through n plus 1, n plus 2, n plus 3, n plus 4. It finds nothing, no mention of the NFT of token ID 1 that belongs to the Bored Ape's smart contract. Now suddenly at n plus 5, it encounters a transfer event that points to the token ID 1 of the Bored Ape's smart contract. Now if we haven't seen that token ID 1 before block n plus 5, that means this is the first time that token ID has been transferred, which means this is the event that corresponds to the minting of that token ID. But what if we already have an instance of this entity that corresponds to the token ID in our subgraph data store? In that case, this condition won't be triggered, and instead we will just update the values. Okay, so what is happening is, if we already have a store for this token ID, that means we have encountered this before, and that means this token ID is simply being transferred from one address to another. So if we look back at our entity, what are the values that we will need to update in case our token ID is transferred from one address to another? We will need to update the block number because we want to keep the record of the last block number where the token ID was transferred, and we'll need to update the new owner field because the ID created and token URI will remain the same. So if we have a store of that token ID in our subgraph database, the token is simply being transferred, and we just update the new owner and the block number fields, and then we save. And again, if it is null, which means we haven't seen that before, all of this will be executed and the new instance will be saved to our subgraph database. Now, working with the property entity is going to be a little different because we're fetching data from IPFS, right? So first of all, we need to define the token URI. So this unique content and identifier is where the whole metadata of the Bored Ape smart contract is located. In fact, I'll just show you. So we copy this content ID, right? We call it the CID, and we go to this, and this is just IPFS slash the CID. And if we click on the token ID, just look at the URL. It's IPFS slash CID. And if we click it, we can access every unique token's specific metadata by appending the token ID to the previous URI. And this is what we get. We get an IPFS URI that corresponds to the just the image, and like you can see it, right? It corresponds to the image, and the rest of it is the attributes, a specific JSON object that outlines the properties of that image. It is made up of the image URI and the attributes JSON object. In this case, we have 1, 2, 3, 4, 5 attributes out of the 7, so that means 2 of the properties will be null, and we need to fetch this and store it in our subgraphs database. Now, after that, we again perform a null check because if we are encountering a specific token ID for the second time, it means we have already indexed the metadata, right? When we saw that token ID for the first time. But if we are seeing that token ID for the first time, for example, we saw the token ID 1 at n+5, that means we need to index all of that data. So in the null check, we make the full URI by concatenating the IPFS hash and the token URI. We have hard coded the IPFS hash here because it won't change, and we get each token URI from the string from the event by event.params.token ID, and we get the full URI. Now this is really important. Using IPFS.cat, we can access all of that metadata from the IPFS data variable. And after that, it really is there's a bunch of code, but the concept isn't that difficult. Let me close a few if statements. So we parse through the IPFS data by converting it into an object, right? Using the JSON class we get from the graph protocol. We access the image and we store it because the image's URI can be converted to a string, and we store it in property.image, which we get from here, and then we parse through the whole JSON array of attributes, and if we perform a if statement check on each of these attributes, right? Because as you can see from here, we have only 5 attributes, but there are 7 possible attributes in a single Bored Ape. So whenever we see an attribute's value as null, we will store it as such. Otherwise, we will add the actual values to our entity. Once that is done, we just do property.save to save permanently this thing to our subgraphs database. We save the file, and that is it. We have now indexed all 3 of our entities by leveraging nothing more than the transfer event from the contract. And once you're done with your mapping file, I recommend you run this command, graphcode and graph build. This will just compile your subgraph, which means it is ready to be deployed. But to deploy our subgraph, we have a few options. Let us go over through all of them so that you have a clear idea of what you have. There, as of now, are 2 main ways to deploy a subgraph. Number 1, you participate in the Graph Protocol's decentralized indexing network to index your subgraphs. It does cost GRT tokens to incentivize indexers to actually index your subgraph, but this way you can stay true to Web3's decentralization ethos. Another option is to use centralized indexing providers. Companies like ChainStack provide their own solutions, while companies like QuickNote participate with indexing providers like Satsuma to give you a convenient experience. Another option you do have, however, is to run your own graph node. Remember, the graph above everything else is an open source initiative. This means you can take the code for the indexer node, compile it, and build it on a system on the cloud, and expose that system's endpoint to build your own indexing service. How cool is that? Now, I won't be going into how to deploy a compiled subgraph. That is just really simple. Just run the graph deploy command with the correct URL. Your indexing provider, if you're using one, will give you the exact command you need to run. If, however, you are interested in learning more about how to work with a local graph node, or you want to learn more about querying data from your subgraph, you can check out the video I will link in the description. Also in the description, I will drop a link to the article I wrote on getting started with subgraph development, just so that you're covered on all bases. If you like this video, feel free to drop in a like or a comment, and I'll be back with more.